Hi, in this video I will show you how to perform an optimization in COMSOL Multiphysics. A while back I made a video series in which I explained how to connect MATLAB to COMSOL. So if you follow that video series you will be able to connect these two software together, and obviously MATLAB has many optimizers. Local optimization, you can do global optimization, different types, GA, simulated annealing, particle swarm optimization, and so on. So in that case, obviously you can, after connecting these two software, use MATLAB optimizers to optimize your problem in COMSOL. But sometimes this takes a little bit time to set up the model and everything. So maybe you prefer a simpler method to do optimization. So that is actually possible. COMSOL itself offers this option. The option that we have in COMSOL actually is only a local optimizer. So if you are really looking for a global optimizer, then you must follow the previous method, which means basically connecting MATLAB to COMSOL. But in case you just want a local optimization, then the method that I'm going to teach you today will be very helpful. Now in COMSOL, we can perform three types of optimization. We have a parameter optimization, we have a shape optimization, and topology optimization. With parameter optimization, it means that your model has several parameters, and then you want to vary those parameters to optimize an objective function. In shape optimization, basically you have a geometry and then one boundary or multiple boundaries. You want to change the shape of them, maybe create a little bit more bend or less bend to optimize an objective function. And in topology optimization, you basically have a region. Maybe you want to remove some part of that region. Maybe you want to add some extra part to that region, change the material. So basically give you a general optimized topology. Now in this video, I will only talk about the first one, which is parameter optimization. And then in the coming videos, we will cover the other type of optimization. Okay, so now I will open COMSOL and will use a benchmark model that I have used previously in my channel. And then we will see how to optimize this particular problem. All right, so I have COMSOL open. I will create a new model, 2D. In this case, I'm going to use an electrostatic model as I used before. So you come to AC/DC, electric field and currents, so electrostatic. You select this model, and then in the study, we select a stationary in this case. Okay, so I select the dimension as millimeter, and here I build a rectangle. So maybe width is 5, height is 2, and then I put a circle in the center of this rectangle. So radius is that much, x is 2.5. Maybe I put a parameter here. So I want to give the radius of this circle as a parameter. And material, we give everywhere air with a permittivity of 1. And in the physics, I assign ground to all these outer boundaries. And I also assign voltage to this circle. Okay, so here we have the voltage. These are the ground. So basically we would have an electric field in this region. So the target for us is to solve this problem and calculate the electric field in this space. And we want to change the value of the r, the radius of this circle, such that maximum electric field in this space is a given value that we want. And we want to achieve that through optimization. Of course, by hand, we can change the value of r in this case and find what would be the value of electric field. But maybe for a complex problem, you don't want to change it by hand, so you want to do optimization, and this is an illustration that will demonstrate. Okay, for the mesh, let me create an edge mesh here on this boundary. Maybe I put some sizes here, maybe custom, I don't know, 0.01 or maybe another 5. Very fine meshes there. Maybe this is not good, so I add size, maybe. Okay, so we have the mesh and we have the boundary condition, potential, ground, everything is good. So if I just normally solve it, so in this case, value of radius is 0.3 millimeter. Okay, so this is the electric potential. We can actually change this graph to get electric field. Come to electrostatic, electric, the norm of electric field. We see that the electric field is maybe something around 2500 volt per meter for this initial value. Now let us consider that we want to calculate a value of R such that the electric field is 2000 or maybe 1500 here. So what could be the value of R? We want to obtain that through the optimization. Okay, so you come to the definition. First, right click on here and we define a probe, boundary probe. I erase all of it and I only select these layers, these boundaries. And I want to calculate electric field over those boundaries. Okay, so electric field is here. And then here maybe I want the maximum electric field. In the previous videos, I explained that the value of the parameter on the boundary is average of the value in these two domains. But because we have equipotential line on these boundaries, so internal structure will have zero electric field. So we have zero electric field here. So if we want to calculate electric field right above the boundary, actually the value will be double than what we have on the boundary. So the real electric field that I'm looking for is actually 2 times this electric field on the boundary. So I multiplied it by 2. Okay, so that is the probe that we defined, which gives us the maximum electric field on this boundary, but because we multiplied by 2, right above the boundary. All right, so now you come to study, right click on the study, and we come to optimization and select first option, optimization. Okay, so here basically there are different models, different solvers that you can use. This is the tolerance. Let us increase the tolerance a bit. The number of iteration will be 1000. We leave it as it is. Okay, so what is objective function? The objective function that we have is actually this value. That's 2 electric field on this region or 2 times electric field on the boundary. We come to optimization and we can add. Okay, so here definition, if you click on definition, this one is there. So the value of that probe. But let's say we want to calculate R in such a way that this objective function is equal to 1500. So I subtract this value from here. So this one minus 1500. I want to minimize this. So let us make this a positive number. So power 2 maybe. Basically, because this type of optimization is minimization, so we want to minimize this function here. And this function will be minimized if the value of the objective function is actually very close to 1500. And that is what we want. We want to have the electric field, maximum electric field 1500 volt per meter. Okay, so what are the parameters that we can change? The parameter is R, so you click here and this parameter. So initial value is 0.3 and then the lower and upper boundary. So let's say lower boundary is this much because this height is totally 1. So upper boundary maybe is 0.98 or maybe this one also 0.2. Not just making it 0 and not to pass this boundary. And in this case, I do not have any constraint. Okay, so let us run this optimization and we see what we get. Here I can click on probe plot to see how the optimization basically works. So the initial point was here and it is now changing the value of R. And for each value of R, it calculates the objective function and basically tries to optimize it. Okay, so now optimization is finished. Let me change this to electric field. We can see that the value of R that the solver found is 0.35. And actually what we see is that maximum electric field is not 1500, which we asked for. So here in the optimization, you remember that we asked for 1500. But what we see here, we have an optimized value of 2000, maybe 500, 2400 or something like that. The reason is actually we will never be able to find a radius such that we can get a value of 1500 for this problem. Because if we decrease the value of this r, so this circle becomes smaller and smaller, and if the radius is smaller and smaller, actually we have a higher electric field here. And if this circle becomes bigger, very bigger, then it becomes very close to this ground electrode, and so again we will have very high electric field in that region. So both boundaries, so if r is very small or r is very big, actually the value of electric field will be very large. So then there is a minimum in between, and that minimum is whatever that is right now it funds. It's at 0.35, and that minimum is around 2400 volt per meter. So we will never be able to get 1500, but actually this value that it gives is the most closest one to the one that we asked for. But now let us assume that we put a number such that it can really find. For example, I put a number of, I don't know, 5000. So we want to find the value of R such that the electric field is 5000. I run the optimization again. Okay, so now the optimization is done, and we can see that if you look at pro plot, you can see that after a lot of change, eventually it converges to 5000 volt per meter, and this is the final result. So actually in this case, we were able to really optimize the problem and find the value that we want. To create electric field of 5000 volt per meter, we found the value of R, which is 0.78. Now, one thing to notice is that the value of this optimized parameter depends on the initial condition that you give. For example, in this case, I mentioned that as the radius of this circle increases, the electric field increases, but also if the radius decreases, the electric field increases. So if I would give another initial condition here, probably I could find another point which is also the optimum and fulfills this condition. For example, let me I give this initial value 0.1 or maybe 0.8, I don't know. Probably this will lead to the optimum point, which is very small, not this one that is very large. Let us try it. Okay, so now optimization is again finished, and this time we see that the value of R here is 0.068 millimeter. And actually our objective function is still the same. We wanted to find a radius in which the maximum electric field is 5000, and this is also the case. But this is another point which this condition is fulfilled. Now, if your problem has multiple parameters or sometimes even one parameter, because this is a local optimization, it can happen that the program only finds a local optima, but the global optima is much better than that local optima. So in that case, maybe you have to use a different initial condition to probe the landscape a little bit better, or connect MATLAB to COMSOL and use a global optimization like genetic algorithm or something similar. But if you want to simply perform a local optimization, you can do it directly in COMSOL. And for parameter optimization, basically this is the method that you have to use. Even if you have multiple parameters, it doesn't matter. You can do the same thing and you will be able to optimize your problem. All right, so that's all for this video. See you next time. Bye.